Hi everyone, so today I will be solving an elliptic partial differential equation with given initial and boundary conditions using the finite difference method. So here we are given the Poisson equation which define over the square domain 0, 1 times 0, 1 and the boundary conditions were given. So our goal is to solve this PDE numerically, display the solution in the table and visualize it using a surface plot. Let's now take a closer look at the MATLAB code that solves the elliptic partial differential equation. So firstly, here n and m define the number of interior points in the x and y directions respectively. We divide the domain 0, 1 times 0, 1 into a grid using h and k. The plus 2 in our grid accounts for the boundary conditions. We initialize the solution matrix W to 0 and generate the full grid using mesh grid. The W matrix holds the solution for u, x, y. Next, we impose the boundary condition. Here, R is the ratio used in the finite difference tensor for the Laplacian. We initialize the coefficient matrix A and right-hand side vector F to set up the linear system which is AU is equal to F. Then, for each interior point, IJ, we construct the finite difference approximation. So for solving the linear system, we solve the system of equations for the unknown u, which contains all the interior values of u, x, y in a vector. We take the 1D solution vector u and assign the values to appropriate grid points in the 2D matrix W. So to view the result, we put f print f so that this part prints the interior grid points and the computed values of u, x, y in a tabular form. And finally, we visualize the result, which I put figure, and the 3D surface plot shows how the solution behave across the domain, clearly rising towards the boundary at x equal to 1, where u equal to y squared. The rest of the edge remains 0 as defined. So in summary, this code takes the elliptic PDE, discretizes the domain, constructs and solves a linear system using the finite difference method, and finally presents the numerical solution in both table and visual form. So here you can see the output of the numerical solution. On the left, we have the computed values of u, x, y at each interior grid point listed in the table format. And on the right, the 3D plot of the solution surface shows the behavior of u, x, y across the domain. As expected, the solution is 0 along most boundaries and it rises smoothly on the right edge, consistent with the y squared boundary conditions. So, this visualization helps confirm the correctness of the numerical method. To conclude, the finite difference method successfully approximated the solution to the Poisson equation with the given boundary conditions. The numerical result aligns well with the expected behavior of the system.
So for the question 2, this question is all about solving a third order initial value problem. So there is given an ODE with the power of 3 with 4 different questions, which is A, solve the given third order initial value problem analytically, B, solve the problem numerically using MATLAB ODE 45 solver by converting it to a system of first order differential equation. C, display the numerical result in a tabular form at a specific time point. And lastly, plot the solution yt over the interval 0 to t to 5. In this task, we solve a third order differential equation using both analytical and numerical approaches in MATLAB. So first, we use symbolic maths to solve the ODE analytically with the solve function, applying with the initial condition given for y0, y prime 0 and also y prime prime 0. Then we implemented a numerical solution using the ODE 45 solver. We converted the third order ODE into a system of first order equations to be compatible with the ODE 45. Next, we display the solution in table format to show values of yt, y prime t and also y double prime t at a specific point. Finally, we plotted yt over the interval of 0 to 5, showing the behavior of the solution visually. This combination of symbolic and numerical technique help us verify the accuracy and behavior of complex ODE solution efficiently. Here, we can see the result of solving the third order differential equation. On the left side, we have the analytical solution displayed as an exact solution of expression involving exponential and trigonometric functions. Below there is a numerical table showing that the value of yt, y prime t, and also y double prime t at a specific time points. This was generated using the ODE 45 solver in MATLAB. So on the right, we have a plot of yt. The graph shows how the solution grows over time, confirming that the function increases rapidly as t approaches 5. This output helps us to understand the behavior of the system both symbolically and also numerically.
Question number 3 is about function. So given question is a create a MATLAB function that calculates the volume and surface area of a sphere given its radius. The radius should be read from the keyboard. The function should return both the volume and the surface area. Then call this function from a main script where the radius is input by the user and display the result. For the part A, write a MATLAB function named sphere underscore calculation dot m that takes the radius as an input and return the volume and surface area of the sphere. Inside this file, we are going to create a function that calculates the volume and the surface area of the sphere. This file defines a function in MATLAB that can be reused to compute the volume and surface area when we are providing the radius. We use the mathematical formula for the volume, which is 4 over 3 pi r cubed, and the surface area is 4 pi r squared. For part B, we are going to write a main script named mainSphereCalculation.m that prompt the user to input the radius, call the function, and display the result. Okay. So first, we are going to prompt the user to input the radius and check if radius is a non-negative. So radius equal to input, enter the radius of the sphere. If radius less than 0, f(f), radius must be a non-negative value and also written then n. Next, we are going to call the function to compute volume and the surface area. Vol area equals to sphere calculation in radius. Lastly, we are going to display the result with f(f) for a sphere with radius in radius, f(f) for the volume with the cubic unit, and f(f) for the surface area in a square unit. So for the output, when the user input a negative value of the radius, the output that come out on the command window will be the radius must be a non-negative value, and there is no answer for the volume and the surface area. Next, when the user input a positive value of radius, the output that come out on the command window is for a sphere with a radius that be entered, and the volume and the surface area will be produced.
In question 4 asks for plotting a 3D graph of a given function with detailed properties. So consider the function z equal to fxy defined by z sine square root of x squared plus y squared. Correct a MATLAB script to plot the 3D surface of the given function over the domain x in -5 to 5 and y in -5 to 5. So customize the plot with the following properties. A. Add a title and axis label. B. Use a color map to represent the height of the surface. C. Add a color bar to indicate the mapping of color to function value. D. Set the view angle to provide better perspective of 3D plot. And the last one, include grid lines for better visualization. This is my MATLAB script for question number 4. Firstly, I define the range for x and y. I use the linspace one. So x equal to linspace -5, 5, 100 semicolon. Y equal to linspace -5, 5, 100. So the -5 is the initial value,
5 is the n value, and 100 is the number of point. Then I create a mesh grid for x and y. So capital X, comma capital Y equal to mesh grid x and y. And then I put the function I put the function, so z equal to sine square root of capital Z dot square plus y dot square. It has dot because it is a function, it is a vector. And now I want to plot the surface. So first I write the figure because I want to create a new figure window to create the surface, and I use surf capital X, capital Y, capital Z to plot the 3D surface. As just now I use mesh grid. And then I customize the surface by adding X label for X axis, Y label for Y axis, and Z label for Z axis. And then I put title for the surface. The title for the surface is 3D plot of Z equals sine square root of x squared plus y squared. And then I change the color scheme for better visualization, and I choose color matte jet. And lastly, at this part, I customize the surface by adding the color bar to indicate scale of the Z value, and view angle adjustment for better visualization. The view angle that I use is negative 30 and 45. And then I enable grid for better visualization and readability, and I just grid on. So this is my output for question number 4 to plotting the 3D graph. So at top we have 3D plot of sec equal to sine square root of x squared plus y squared as a title, and then we have a grid at the graph as we enable grid for better visualization, and then we have x-axis, y-axis, z-axis, and at the right side of of the the right side of the graph we have the color bar as it indicates the scale of z value. And as we can see, the graph turns like this. The color of the graph turn like this because as we change the color scheme as to color matte jet.